You know, in our digital lives, we're constantly being asked to prove who we are or what we own. But what if? What if you could prove you have something without actually revealing any personal details at all? Well, today we're going to dive into the really elegant structure that makes this whole idea possible. Just think about that for a second. It sounds like a complete paradox, doesn't it? In this digital world we live in, we're always running into this problem. We need to verify stuff, but we also desperately need to protect our privacy. So how in the world can you do both of those things at the same time? And that really gets us to the heart of what we call the digital trust problem. It's this constant tug of war, right? Between proving something is true, like, say, a transaction happened or you own an asset, and keeping all the sensitive details about that very thing completely under wraps. This is the big puzzle so many modern systems are trying to crack. So how does a system like Harpo even begin to tackle this? Well, the answer lies in this really brilliant data structure known as the Merkle tree. And it's not just some random component, it's the absolute foundation, the bedrock on which all the trust is built. Actually, the source material calls the Merkle tree the system's trust backbone, and I think that's just the perfect way to put it. It really captures what it does. It's not just sitting there holding data, it's providing the structural integrity for the entire security model of the system. So what is a Merkle tree, really? At its heart, it's a super clever way of organizing data. In a system like Harpo, it takes all the individual transactions, which are called commitments to help protect privacy, and it arranges them into this highly secure, totally verifiable structure. Okay, so how does this trust backbone actually work? I know it might sound complicated, but we can actually break it down into a pretty simple three-step process. Let's start with a helpful way to picture it. I want you to imagine that every single piece of data leaves a unique digital fingerprint. In the tech world, we call this a hash. Now, the Merkle tree takes all of these individual fingerprints, which are at the bottom, and it combines them, going upwards, layer by layer, until you get one single master fingerprint at the very top of a pyramid. And this three-step flow is really where it all comes together. So first, each of those commitments we talked about is like a leaf at the very bottom of the tree. Second, the digital fingerprints, the hashes of these leaves, are paired up and combined, over and over, all the way up until they form one single hash at the top. That's the Merkle root. And finally, this is where the magic happens. Using something called a zero-knowledge proof, which is just a cool cryptographic way to prove something's true without revealing the information itself, you can confirm that your leaf is in that tree, all without ever showing anyone what your leaf actually is. Pretty neat, right? Okay, so we've gone to all this trouble to build this intricate digital pyramid. What do we actually get out of it? Building a structure like this gives us some incredibly powerful assurances. You see, the power of that single Merkle root, that one fingerprint at the top of the pyramid, it gives us three fundamental guarantees. And these guarantees are the pillars that make the entire system trustworthy. First up is verifiability. And this takes us right back to the question we started with. Because of the way the tree is built, you can prove your transaction is included in the whole system just by pointing to that Merkle root. You prove ownership, but you never have to show what you own. It's proof without exposure. The second guarantee is efficiency. Now, you might think that proving something against a huge database with millions of transactions would be super slow and clunky, right? But with a Merkle tree, the proofs are incredibly small and fast. They're lightweight, and that's what makes the whole system run smoothly and scale up. And finally, we have immutability. Once a commitment gets added to the tree and becomes part of that Merkle root, it is locked in, set in stone. If you try to change or remove it, you'd change its hash, which would then change every single hash, all the way up to the root. You'd end up with a completely different master fingerprint, and the system would immediately know something's fishy. Your data is secure and permanent. So let's zoom out for a second. We've got verifiability, efficiency, and immutability. When you put these three powerful guarantees together, what's the big picture? What does this actually enable for the system as a whole? The result is a system that can do three absolutely critical things. It has scalability because those proofs are so efficient. It creates trust because the data can't be changed and it's all verifiable. And most importantly, it does all of this while keeping every user's data completely and totally private. It solves the paradox we started with. And that leaves us with a really fascinating thought to chew on. This isn't just about one system or one piece of tech. It's a blueprint. If we can fundamentally structure our data to be both private and verifiable, to create trust with math, algorithmically, what does that mean for the future of, well, everything? Digital interaction, finance, our very identity. What kinds of new worlds can we build on a foundation like that?